So let's talk about cross section. In a simple language, let's make that the full name: effective cross section. When I say effective cross section, I mean it's the probability of neutron to interact with nucleus or nuclei. If we talk about single nucleus, we call that actually the microscopic cross section. So the probability of interaction with a single nucleus, we call that microscopic cross section. If we talk about large number of nuclei, we call that actually the macroscopic cross section. So be careful if you talk about single nucleus, which is not our case, because we're going to have a fuel pellet that has large number of nuclei. So we more into the macroscopic one. The microscopic cross section area, we call that actually sigma small, and the macroscopic, we give it actually the Latino symbol, the Latin symbol sigma, capital. Okay, and they are actually related as we're going to show here. So now let's focus on interaction with a single nucleus. What type of interaction we would have? So let's start with two major categories here. The first major one is actually, let's do here neutron interaction. And we're going to call that one the total interaction. Total interaction. And we're going to give actually the symbol sigma subscript T. So the probability of total interaction between neutron and single nucleus. Total interaction can be of two different types. The first one is actually absorption. And the second one is actually scattering. What does that mean? It means that you have a nucleus, you're going to hit the nucleus with neutron, and that nucleus will absorb that neutron inside. The second one, you're going to hit the nucleus with neutron, and this will bounce back or maybe get redirected, but it's not going to be absorbed. Okay? That's what we meant by absorption. Is going to be contained inside the nucleus, or it's going to scattered away or reflected back by the nucleus. Okay? When you do the absorption, you may actually have nothing happen. So the neutron will be absorbed, but the nucleus, it stands still. It's not going to move, right? And that what we call it what? Capture. So the nucleus will capture the neutron without any change in anything, as if nothing actually happened. The other chance is the nucleus will actually absorb that neutron and will go into fission. And that's what we're looking for. So the probability of nucleus to absorb neutron, we're going to call that sigma absorption. Then under sigma absorption, we maybe have sigma capture or sigma fission. So if I want to calculate the probability of absorption, it's going to be the summation of the probability of capture plus the probability of fission. Okay? Then go to the scattering. We're going to call that sigma scattering. By the way, if you add sigma absorption to sigma scattering, it's going to give you sigma total. So when you add subcategory, it's going to give you the sigma for the upper category. Now let's look to the scattering. Scattering means that neutron will hit the nucleus. It's not going to be absorbed. It's going to be reflected back, or it's going to be scattered away, right? When he hit the nucleus, we have two chances. The first one is to cause elastic scattering. Means that collision doesn't change the level of energy of either the neutron or the nucleus. So the nucleus is not going to be changed. Level of energy is not going to change. That's why we call that elastic collision, right? Or elastic scattering. And this will have sigma elastic. The other type is the level of energy will be impacted by that collision, and we're going to call that inelastic scattering. Inelastic scattering, sigma inelastic. Again, you add up the two probabilities, is going to give you the upper one. You add these two sub probabilities, going to give you the upper one. You add these two together, is going to give you the total. So I can say here, sigma total is actually sigma absorption plus sigma scattering, and sigma absorption itself is actually sigma capture plus sigma fission, and sigma scattering is simply sigma elastic plus sigma inelastic. Okay, that's the probability by addition here. By the way, there is a third type called transmutation. And this is always neglected. Just in case you are reading a book or a different reference, you maybe find the third category here, but this is not what we're interested in. That's our big interest here. That's what we're looking for. Chance or the probability of neutron to be absorbed by the nucleus, and that absorption will cause fission. That's what we're looking for, okay? So we are going from absorption all the way to the fission. That's what we're looking for. We don't look to the other things here, okay? So keep that in mind. How do we measure the sigma or sigma small? Remember, we are talking about sigma small. Sigma small has a unit of area. Okay. And the standard unit for sigma is actually called the barn. And one barn is simply 10 to the minus 24 centimeters square. Okay, so when you open any book, you will find that these are all tabulated values here. These are in tables. So you will find tables that include the probability of absorption, of fission, of scattering for single nucleus of uranium-235, plutonium-239, whatever it is, depending on the isotopes. But these are in tables all the time. Okay. The unit is usually given in a barn. You can convert barn into centimeter square by multiplying by 10 to the minus 4. Now, this is the probability of interaction with a single nucleus. What about a fuel pellet or a volume that contains large number of nuclei? How to calculate the probability of interaction here? So we are looking for macroscopic cross-section. That's sigma capital. Sigma capital is related to sigma small by something called n, whereas n is called the number density. Okay? And the number density, n, is given by rho times AV divided by m. So n is the number density, and the number density has the unit of number of nuclei, which has no units. So that's no units per unit volume, which is usually centimeter cube. So the final units of n is actually nothing, 1 over centimeter cube. That's the unit. Rho is the density. That's the element density. Which has a unit usually in gram per cubic centimeter. I'm giving you the unit that you're going to see in tables and information in problems. Then AV is Avogadro's number, which is 6.0225. You can make that 3, 10 to the 23rd. It's atom per mole, which is the number of atoms per unit mole, which the final unit is 1 over mole, because number doesn't have units here. Then you calculate the number density here. You look to the final, that's going to be gram per cubic centimeter. Avogadro's number is 1 over mole. Then the molar M is the molar mass. with the unit of atomic mass unit or atomic mass unit, which is equal to gram per mole. So if you put that unit here, that's gram per mole. Mole goes away, gram goes away. So it's going to be actually number of density is going to be the number of nuclei per unit volume. So it's going to be 1/centimeter cube. That's N. Now, if you want to get the unit of capital sigma, it's going to be 1/cubic centimeter multiplied by sigma has a unit of centimeter square or bar. You can convert that. So it's going to be actually the final unit of sigma is 1/centimeter. So it's 1/distance, right? It's 1/distance. Okay. When you flip that number, you got what we call it lambda, which is the mean free path, which is the distance neutron will travel between two collisions. That's the distance of that neutron between one fission to the other one, and so on. So this is how you calculate actually sigma. The beauty about large sigma here, it can be broken into number one, what sigma here? Sigma here is depending on that sigma. For example, if you want to get the macroscopic fission, you have to put the microscopic fission. If you want to get scattering, you have to put scattering. If you want to get total, you have to put total. So this capital sigma is actually following what small sigma you are using based on the chart that we discussed in the previous slide. Okay, that's number one. Number two, you can actually calculate sigma for compounds. Remember, sigma is for element. Sigma small is for element. Okay, now, for example, let's assume that I want to get the macroscopic cross-section area of H2O. This will be sigma for hydrogen plus sigma for oxygen. Then you take that and you got number density times sigma for hydrogen plus N of oxygen, that's hydrogen, sigma oxygen. And again, if you put that fission, this will be fission. If you put scattering will be scattering. If you put total will be total. So the beauty about capital sigma, you can do that for compounds as well. So I can write that big sigma here as a combination of N1 sigma 1 plus N2 sigma 2 plus N3 sigma 3 and so on, depending on how many components you have for that compound here. So that's the microscopic and macroscopic cross section. So let's give a quick example here to learn how to calculate actually sigma. And you will find that there is a set of tables that we use all the time. And you should have a copy of these tables actually in the course web page, so you can actually reach out and use it. For example, I would like to calculate sigma H2O. I was given density equal, I need to calculate that, and I need to calculate the total. So I need to get the total macroscopic cross-section for H2O if the density is given by 1 gram per cubic centimeter. Okay, again, H2O is a compound, so let's do the solution here. So I cannot get that from a table only for elements. So I can find sigma small for hydrogen, I can find sigma small for oxygen, but I cannot find sigma small for H2O. Right? So what I'm going to do, I'm going to break down that sigma into N1 sigma 1 plus N2 sigma 2. Now, and I need that total. So that has to be sigma total. That has to be sigma total as well. So this will be number density of hydrogen times sigma total of hydrogen plus number density of oxygen, one atom of oxygen, times sigma total of oxygen. Sigma total hydrogen, that's sigma total for element, and that's sigma total for oxygen, that's an element, or 1O, that's an atom. I can find these values in tables. Let me get my table copy here. So that's the table that we're going to look through. So you will find that, for example, this is hydrogen here. and this is oxygen here. Then if you look into the hydrogen, you will come to that last column here. This is the cross section. This is sigma small. This is sigma small. And you will find that this is sigma absorption and this is sigma scattering. And I know that if I add up these two, it will give me what? Sigma total. So sigma total is sigma absorption plus sigma scattering. So for example, for hydrogen, sigma absorption is 0.332, sigma scattering is 38, and the unit is barn. So I will add up these two numbers. I can get the total microscopic cross-section for hydrogen. We do the same for oxygen. I have sigma absorption, sigma scattering. I will add up these two numbers to get sigma total, and the two numbers are given here. So I can simply get sigma total hydrogen by adding 0.332 plus 38. And for oxygen, I will get that 0.0002 plus 4.2. And each one of them will be of the unit of bar. It sounds like I'm going to need everything in centimeters as a unit of distance. So I'm going to convert that later on. So if you do that, you can actually simply calculate the total, sigma total hydrogen is simply 38.332 times 10 to the minus 24. That's centimeter square. Then sigma total of oxygen is going to equal to 4. Let me double check if how many zeros are here. It's super tiny. I think 3 zeros. So that's 0, 0, 0. So it's going to be like 4.200, maybe 2, right? Times 10 to the minus 4 centimeter square. Okay. So I got sigma total here. So I have this sigma total. I have this sigma total. Okay. Now, how to get the number density of each one of these atoms here? How to get N for hydrogen? Okay. How to get the number density of hydrogen? This is the equation is rho Avogadro's number over the molar mass of hydrogen. Okay. So this is hydrogen. This will be hydrogen here. Okay. So that's what we need to calculate. Do we know actually what's the density of hydrogen? Rho of hydrogen. If I use that for oxygen, that's Avogadro's number. Do we know the density of oxygen? No, we don't have these data. Unknown. But I know everything about H2O. So I can calculate the number density of H2O equal density of H2O, which is given to you in the problem. That's density of H2O multiplied by Avogadro's number times the molar mass of H2O. Density of H2O is 1, 6.023 10 to the 23rd. That's Avogadro's number over the molar mass of H2O is going to be the molar mass of H2 plus the molar mass of oxygen. This will be 2 times 1.008 plus the molar mass of oxygen is actually 15.9999. Where these numbers are coming from, you would be provided a table, and that table actually includes here. Look at this. Here is the molar mass of hydrogen, and here's the molar mass of oxygen. Okay, and try to make the significant digit equally for each one of them. So I put 1.008. I put this one 15.999. You do that, you can get actually the number density of water. What this number would be, let me check my calculation here. I got that number to be 0.3033 times 10 to the 24. This is molecules of H2O per unit volume, which is centimeter cube. I know that each water molecule has 2 atoms of hydrogen and 1 atom of oxygen. So if I want to get the number density of actually hydrogen, I will multiply 2 by 0.0334 times 10 to the 24. This will give me the number density of hydrogen. This will be hydrogen atom per centimeter cube. And if I multiply 1 times 0.0334 10 to the 24th. This will give me number density of oxygen atoms per centimeter cube. I will take this into this equation. I will take this into this equation here. And I got these two values as well. Now I can substitute and calculate the capital sigma for H2O, which is a compound, by knowing the details of the component of that compound. The final number I'm getting here, I'm getting sigma total to be 2.71 over centimeter. Again, that's the unit of sigma. Okay. Can you calculate actually from this? Can you get me sigma small total for H2O? Remember, this is not tabulated. This is compound. Yes, I can say that sigma total H2O is simply sigma small total H2O, which is not available in the table, multiplied by the number density of H2O. You already got that number density of H2O. You already got this number here from the broken equation here. I can calculate this one. So sigma total for H2O is coming to be actually 81 bar. This is just an additional request that you may experience in a homework problem or anything like that. So I use that sigma here. Then number density I already calculate. I can actually calculate sigma H2. I cannot calculate that individually. I cannot break it down because sigma only capital can be broken down into the component of the compound, but sigma small cannot be done. But I can do some estimation for what's a total microscopic cross-section for H2O from that example. This is just a very quick example. You may not actually see any similar problem anywhere else. I'm just showing you how we can use the formula for the capital and small sigma to do some quick math in this problem.